topic is effect of source inductance on single phase rectifier. Okay. So effect of source inductance on a single phase rectifier. So it a figure below shows the so this figure shows the single phase full wave converter circuit with a source inductance. Okay. So full wave converter with a source inductance. For simplicity, it can be assumed that a converter operates in a continuous connection mode. Further, it has been assumed that the load current ripple is negligible and the load can be replaced by a DC current source, the magnitude of which equal to average load current. So figure shows the corresponding waveforms. So it is assumed that the thyristor at starting thyristor T3 and T4 were connecting. Here at starting thyristor T3 and T4 will be conducting at T equal to 0 and T1, T2 are fired at omega T equal to alpha. So this figure shows the single phase full wave converter with a here with a source inductance L, and at starting at time constant T equal to 0, T3 and T4 will conducting, and triggered at omega T equal to alpha, then T1, T2 will be conducting. Okay. So for simplification, we have assumed that it is a continuous connection mode. Further, it has been assumed that the load current ripple is negligible and the load is replaced by a DC current source. So load is replaced by DC current source. So there were no source inductance in T3 and T4 would have commutating as T1, T2 will be turned on. So the input current polarities would have changed instantly. However, if a source inductance present in a commutation and a change of input current polarity can't be instantaneous. So therefore, when T1 and T2 are turned on T3 and T4 does not commutate immediately. Instead of some interval of 4, thyristor continues to conduct as shown in figure. The intervals called overlap interval. So here T3 and T4 will conducting at T equal to 0. So here there is no source inductance for this conduction. So it will be immediately turned off, and after that the T1 and T2 will be turned on here. Okay. So we have to see the full wave converter output with the source inductance. Due to source inductance, here overlaps will be there. So this is input waveforms Vi and current input II. So here the ripples of output current will be negligible. So here at starting T3 and T4 will be conducting, and at omega T alpha T1 and T2 will be here. This is the source inductance will be there. Here T1 and T2 will be conducting. After that again T3 and T4. Here the overlapping angle mu will be there. So here overlaps the due to source inductance overlapping will be there. So this is V naught. So at starting and negative side will be starting and it will be continuous. Here this is a source due to source inductance. Some overlapping will be there. So the output waveforms will be like this. And VT1. So VT1 means thyristor voltage. VT1 will be like this. So at T equal to 0, VT1 will be high, and after near to 2 pi where T3 and T4 will be turned off, then VT1 voltage will be there. Here mu is the overlap angle. Okay. And next we have to see during overlap interval the load current freewheels through the thyristor and the output voltage is clamped to 0. On the other hand, the input current start to changing polarity. The current through T1 and T2 increases and T3, T4 current decreases. At the end of overlap interval, current through T3 and T4 becomes 0 and they commutate T1 and T2 start conducting in the full load current. So the same process repeats during commutation from T1 to T2 and T3, T4 at omega T equal to pi plus alpha. So in the figure, you have to see that this process at starting T1 and T2 conducting. After that T3, T4 will be turned on at omega T equal to pi plus alpha. The T3 and T4 will be turned off. So it is clear that commutation is overlap, not only reducing the average output DC voltage, but also reduces the extension angle gamma. So here, which may be cause the commutation failure in the inverting mode of operation if alpha is very close to 180 degrees. So in the following analysis, an expression of overlap angle mu will be determined. Okay. So equivalent circuit of converter during overlap period. So here we want to calculate the overlap angle mu. So from the figure, you have to taken the equation L into di by dt equal to Vi for alpha less than or equal to omega t plus mu, and II into omega at angle of omega t equal to alpha equal to minus I naught. So here II equal to I minus root t into Vi by omega L cos omega t. Here I current I at an angle of omega t equal to alpha I. So capital I minus root 2 Vi by omega L cos alpha, that implies minus I naught. So here uh, I equal to root 2 Vi by omega L cos alpha minus I naught, and here small I equal to root 2 Vi by omega L and cos alpha minus cos omega t minus I naught at omega t equal to alpha plus mu and II equal to I naught. So at an angle omega t equal to alpha plus mu, so small II equal to I naught. Next, you have to calculating II. So small II. So this is input current equal to capital I minus root 2 Vi by omega L cos omega t. So here II at an angle of omega t equal to alpha. So I minus root 2 Vi by omega L cos alpha, that implies minus I naught. So here I equal to root 2 Vi by omega L cos alpha minus I naught. So by simplifying this, II equal to root 2 Vi by omega L cos alpha cos omega minus cos omega t into minus I naught at omega t equal to alpha plus mu II equal to I naught. So I naught equal to root 2 Vi by omega L cos alpha minus of cos of alpha plus mu minus I naught. So cos alpha minus cos alpha plus mu equal to root 2 omega L by V naught into I naught. So V naught equal to 1. So from the circuit V naught equal to 1 by pi integral of alpha to alpha plus pi Vi d omega t. So by simplifying these equations, 1 by pi integral alpha plus. So or we have to write 1 by pi integral alpha plus mu to pi plus alpha root 2 Vi sin omega t. So root 2 Vi by pi cos of alpha plus mu minus cos of pi plus alpha. So root 2 Vi by pi cos alpha. So cos alpha plus cos alpha plus mu. So by simplifying this equation, we get cos alpha plus mu. So V naught equal to 2 into root 2 Vi by pi cos alpha minus cos of alpha plus mu. So V naught equal to 2 root 2 by pi Vi cos alpha minus 2 by pi omega L I naught. So the equation can be represented by the following so this equation can be represented. So the above equation represented in the following circuit. So V into V naught equal to 2 root 2 by pi Vi cos alpha, and here R equal to 2 by pi omega L. So equivalent circuit of a given equation. So equivalent circuit representation of the single phase full control rectifier with a source inductance. Okay, so by simple equivalence circuit, and above figure represents this single phase full wave controlled converter with a source inductor as a practical DC source, as far as its average behavior is concerned. So the open circuit voltage of this practical source is equal to average DC output voltage of an ideal converter. So operating at an firing at firing angle alpha. So the voltage drop across the internal resistance will be RC. So represents the voltage lost due to overlap. So shown in figure. So the hatched portion of waveform. So therefore, this is called commutation resistance. Although this resistance accounts for a voltage drop, currently there is no power loss associated with this resistance, since physical process of overlap does not involve any power loss. So therefore, resistance should be used carefully where the power calculation will be involved. Okay. So we have to see some example problems. For a single phase full wave controlled bridge connected in RLE load, the source voltage will be 230 volts, 50 H. Average load current will be 10 amps. Continuous so it's continuous mode over a working range of R equal to 0.4 ohm and inductance L equal to 2 millihenry. Compute a firing angle for E equal to 120 volts, firing angle E equal to minus 120 volts, and in case output current is constant, find the input power factor for both parts. So it is a continuous mode of operation. So and we have take here it is given as single phase full controlled bridge converter with RLE load. Okay. So its first condition is firing angle E equal to 120 volts. So full wave converter operating at a controlled rectifier. So average output voltage V naught equal to E plus I naught R. So 2 Vm by 5 cos alpha equal to E into E plus I naught R. So here E into 2, here Vm equal to root 2 into 230 volts. So Vm equal to root 2 into Vs. So that substitution 2 root 2 into Vs means 230 volts by 5 cos alpha equal to 120 plus, here I naught will be given as 10 amps and ohm resistance will be 0.4 ohms. So it will be 124 volts. Here by simplifying, we get alpha equal to 53.21 degrees. So firing angle at 120 volts, firing angle will be 53.21 degrees, and power loss from a AC source to DC load. So power flows from AC source to DC load. And next conditions, minus 120 degrees full wave converter operating control rate. So same 2 Vm by 5 cos alpha plus E plus I naught plus R. So by substituting above values, here same in the condition, same in the condition minus 120. So 2 root 2 into 230 by pi cos alpha equal to minus 120 in plus 10 into 0.4. So by simplifying this, alpha we get 124.1 degrees. So for alpha equal to 124.1 degree, power flows from DC source to here, angle will be 124. So above 100 degree. So the source power flows from DC to AC source. Here it will be given angle will be minus. So it will be DC source to AC source. For a constant load current, RMS value of load current will be I naught R equal to I naught, and that is 10 amps. So Vs into I naught R cos pi equal to E I naught plus I naught square R. So for alpha equal to 53.21 degrees, cos alpha will be calculated. So by simplifying this, we get cos alpha equal to 0.53 91 lagging, and for 124 angle cos alpha equal to 0.5043, that is lagging. So this is power factor for a constant load current. Next we have to take another problem. This is about numerical problem for a single phase full wave control bridge rectifier with RLE load. So next we have taken another. So here so up to now we learn single phase half wave, full wave with R load, RLE load, a freewheeling diode, and source inductive. Next we discuss three phase. So same for what we learn in single phase, that's our we learn it in three phase. So three phase half wave rectifier with R load, R load, and RLE load, and three phase full wave rectifier with R load, RLE load, and freewheeling diode we learn. So at starting operation of three phase half wave rectifier with R load and RLE load. So this is a circuit diagram. Three phase half wave rectifier with a load resistance. So this is it. So here T1 and T2, T3, here the load will be connected. So it will be operated in two modes of operation. So next, this is a circuit diagram, and next you have taken the waveforms, input and output waveforms of three phase half wave rectifier. So three phase half wave rectifier at starting T3, T1. So here T1 and T2, T3 will be there. So here three phase will be there. So at starting T3 will be turned on, and after that T1 will be turned on, and after that T2, and again cycle will be repeated T3, T1 and T2. Here this is a three phase input waveform. See here we have RYB. Three phases will be there, and VAB. Here we have VAN, VBN, VCN. Voltages will be there. Okay. So output voltage V0 will be in continuous mode of operation. So V0 will be in continuous. There is nothing will be there. So it will be continuous mode, and I0 also will continuous load current will be there, and here source current at so source current will be gained when their thyristors will be thyristors will be commutating, then it will be obtained source current 5 plus 5 by 6 plus alpha. So here at 5 by 6 plus alpha to 5 pi by 6 plus alpha, here it will be obtained. After that after that 3 pi will be, it will be obtained. So current through T3 it will be there. Okay. So three phase supply voltage equations. So we defined as a three line neutral voltages in three phase voltages as follows. So VRN equal to VAN equal to VM sin omega t. So where VM is the maximum voltage. So next RYN. So it's a neutral voltages RYN, that implies VBN, that equal to Vm sin of omega t minus 2 pi by 3, and Vbn equal to Vcn equal to Vm sin of omega t minus 4 pi by 3. Here three phase half wave converter combines a three single phase half wave controlled rectifier in one single circuit feeding a common load. So thyristor T1 in series with one supply phase winding AN acts as one half wave controlled rectifier. The second thyristor T2 in series with a supply phase winding BBN acts as a second half wave controlled rectifier. The third thyristor T3 in series with a supply phase winding acts as a third half wave controlled rectifier. So the three phase input voltage is supplied through a star connected supply transformer as shown in figure. So the common neutral point of supply is connected to one end of load while the other end is of load connected to the common cathode points. When the thyristor T1 is triggered at omega t equal to pi by 6 plus alpha, that implies 30 plus alpha. And the phase angle VAN appears across the load when T1 conduct, and the load current flows through the supply phase winding AN, and through a thyristor T1 as long as T1 will conduct. So when thyristor is T2 is triggered at 5 pi by 6 5 pi by 6 alpha, T1 becomes reverse bias and turned off. The load current flows through the winding thyristor. So supply phase winding BN. When T2 conducts, the three-phase voltages VBN appears across the load until the thyristor T3 is triggered. When the thyristor T3 is triggered at 3 pi by 2 plus alpha, that implies 270 degrees plus alpha. So T2 is reverse bias and hence T2 is turned off. The phase voltages VAN appears across the load of when T3 will be conducting. Okay. So when T1 is triggered again at the beginning of the next input cycle, the thyristor T3 is turned off and it is a reverse biased. So naturally, as soon as T1 is triggered, the figure shows the three-phase input voltage and output voltage appears across the load. So the load current assuming constant and ripples free load current. High inductive load and then current through a thyristor T1. So for pure resistive load where the load inductance will be 0 and triggered angle alpha is greater than pi by 6, the load current appears as a discontinuous load current, and each thyristor naturally commutated when a polarity of corresponding phase supply voltages will be reversed. So each thyristors will be discontinuous naturally by so by correspond thyristors naturally commuted, polarity of the corresponding phase supply voltages will be reverses. So the frequency of output. So here ripple frequency of three-phase half-wave converter is FS, where FS is the input supply frequency. So here three-phase half-wave converter is not normally used in practical converter system because disadvantages that supply current waveforms contain DC components. So that supply current waveforms have a average or DC value. So by to derive an expression for average output voltage of three-phase half-wave converter for continuous load current. So the reference phase voltages is VRN, VAN, VM sin omega t. So the triggered angle measured from the crossover point of three-phase supply voltage waveforms. When the phase supply voltage VAN begins in a positive half cycle at omega t equal to 0, the first crossover point appears at omega t equal to pi by 6 radians, that is 30 degrees. So the triggered angle alpha for the thyristor T1 is measured from the crossover point at so the thyristor T1 is forward bias during period omega t equal to 30 degrees to 150 degrees when the phase supply voltage VAN has a higher amplitude than the other phase supply voltages. Hence T1 can be triggered between in the 30 degrees to 150 degrees, and when thyristor T1 is triggered at a triggered angle of alpha, the average or a DC voltage for a continuous load current is calculated by using the equations. V average equal to 3 by here 3 phase will be there and 2 pi up to 2 pi will be there. Here we have triggered pi by 6 plus alpha to 5 pi by 6 plus alpha Vn sin omega t d omega t. So 3 Vm by 2 pi minus cos alpha and pi by 6 plus alpha to 5 pi by 6 plus alpha. So 3 root 3 Vm by 2 pi cos alpha. So 3 Vm, so 3 Vm by 2 pi cos alpha, that is V average, and operation of three-phase half-wave control rectifier with R and RL load. So circuit diagram of three-phase half-wave controlled rectifier. So here three-phase Three-phase half-wave control rectifier. So here T1, T3, T5 and here diodes D2, D6 and D4 will be there. Starting T1 and D2 will be connecting. After that T3, D6 and after that T5 and D4 will be connecting. Here three-phase half-wave rectifier. Circuit diagram will be there and three-phase half-wave control rectifier output voltage waveform with the different trigger angles. Here we are using R load. Here three-phase will be there. So three lines VAN and VBN and VCN. So this is VAN and this is VBN and this is VCN. So here alpha equal to 0. So at an angle of alpha equal to 15 degrees, the output voltage will be like this. And here at 15 degrees, the thyristor T1 and D2 will be conducting after uh, when it will be triggered 30 degrees. So the T1 and D2 will be conducted at 30 degrees. At 60 degrees, so at 60 degrees, when we triggered thyristor at 60 degrees, so T1 and D2 will be conducted at 60 degrees. So at an alpha equal to 60 degrees, the waveforms will be like this. So it will be R load. So three-phase half-wave converter can be connected to a form of three-phase half-wave converter simply as three-phase semi-converter. Okay, so three-phase half-wave converter is similarly three-phase semi-converter. Uses a three SCRs T1 and T2. T, T1, T3, T5 and diodes D2, D4, D6 in the circuit as shown in above. When any device conduct a line voltage is applied across the load. So line voltages are necessary to draw a phase shift between the two line voltages is 60 degrees and between the two phase voltages in 120 degrees. Each phase and line voltage in a sine wave with the frequency of 50 Hz. So RYB are a phase voltages with respect to N. In case of three-phase half-wave controlled rectifier with a resistive load, the thyristor T1 is triggered at omega T equal to 30 degrees plus alpha and T1 conducts up to 180 degrees and pound radians. So when the phase supply voltage decreases to 0, the load current falls to 0 and thyristor T1 is turned off. Thus T1 conducts from omega T equal to 30 plus alpha. So that means 30 plus alpha to 180 degrees. So when at when T1 will be turned on at 30 degrees and it will be conduct up to 180 degrees. Okay. So hence the average DC output voltage three pulse converter and three phase half wave control rectifier is calculated using this equation. So average output voltage V average equal to 3 by 2 pi pi by 3 plus alpha to 2 pi by 3 Vm sin omega t plus pi by 3 2 pi by 3 plus alpha Vm sin omega t. Here we are taking, so at starting it will conduct pi by 3 plus alpha to 2 pi by 3 and pi by 3 to 2 pi by 3 plus alpha. So by simplifying this we can get 3 Vm 3 Vm by 2 pi 1 plus cos alpha. So this is input and output waveforms of single phase, three phase half wave control rectifier with R load. So in R load we have continuous output voltage will be there. So at 30 degrees, so this is so we have taken here output waveforms will be obtained, it will be marked in red color. So it is at 30 degrees, the output voltage will be like this. So it will be conducting from 60 to 60 degree. So here it will be at 30 degrees it will be starting and it will be conducting up to 180 degrees. So and after that it will connecting 180 to 300 and 300 to 420. So at alpha equal to 30 degrees. After when alpha equal to 60 degrees, we have triggered, then it will conducting 60 degrees to 180. So 60 degrees to 210. Up to 210, it will be conducting. So the output waveforms will be like this. And at alpha equal to 90 degrees, the output waveform will be obtained, will be like this. So these are the input and output waveforms of three-phase control rectifier with alpha equal to 30, alpha equal to 60, and alpha equal to 90 degrees. So we had taken one example for three-phase rectifier. Through three-phase semi-converter feed power to a resistive load of 10 ohms and firing angle delay of 30 degrees. The load takes 5 kilowatt. Find the magnitude per phase of input supply. So here V average equal to 3 by 2 pi minus pi by 6 of alpha to pi by 6 Vm square sine square omega t plus pi by 6 to pi by 6 plus alpha to Vm square sine square omega t d omega t whole power omega 2. So this is RMS voltage plus three-phase semi-converter. So by simplifying this, 3 Vm square by 4 pi, 3 Vml square by 4 pi omega t plus sine 2 omega t by 2 into pi by 6. So it will be applying minus pi by 6 minus alpha to pi by 6 and omega t plus sine 2 omega t by 2. That will be in the limits of pi by minus pi by 6 to pi by 6 plus alpha. So V naught R equal to VML by 2 root of 3 by 5 to 2 pi by 3 plus root 3 by 2 1 plus alpha cos 2 alpha whole power 1 by 2. So this is VRMS voltage. By substituting above values, so in this equation alpha equal to 30 degrees and P equal to V square by R. So P equal to V square by R. By substituting this, we get Vs equal to 170.67 and V phase equal to 101.43. Okay. So thank you. So today we will discuss single phase single phase rectifier with a source effect of source inductor and single phase rectifier and three phase control converter with R load or RLE load. Okay.